This 80-year-old hydropower plant in Salido Valley in West Sumatra was not in operation for a long time, from 1995 till 2007. My Climate, a non-profit foundation selling carbon offsets, has supported the restoration of Salido Kessel mini hydropower plant. Micro hydropower is gentle to the environment and can be used to replace the fossil fuels in rural areas.
Saya jual dengan PLN sampai PLN memutuskan tidak mau beli lagi tahun 95. Tapi nyatanya itu mereka itu sering diprotes masyarakat juga, sebentar mati ya.
The government electricity company, PLN, started to buy cheaper electricity from diesel power plants. At that time, it was not economically viable to run the micro hydro. Until 2002, the diesel was heavily subsidized in Indonesia. Now the demand for hydropower is increasing.
It really started to change, firstly with the introduction of the small private power producer, renewable energy producer program, which was introduced by the Indonesian government in 2002. And at around the same time, following the economic crisis experienced in the late 90s, the government started to apply a policy of reduction of subsidies, primarily on diesel fuel. So those two factors combined to start to create a more conducive environment for investment in renewable energy projects.
PT Entec renovates the Salido Kessel mini hydropower plant. In 2006, the restoration of the plant started and lasted for 1.5 years. The first out of 3 turbines was restored.
Selama pekerjaan 1,5 tahun kita di sini dari PT Entec memperkerjakan orang lokal sebanyak 20 orang ya. 20 orang, tapi kadang-kadang kita bisa tambah sampai 30 orang. Pekerjaan sipil, pekerjaan elektrikal, pekerjaan mekanikal. Nah, kita di sini proses untuk pekerjaan mekanikal tidak bisa dilaksanakan di Sumatera Barat ya. Karena ya mungkin karena Sumatera Barat ini adalah kota budaya ya, bukan industri. Jadi kita lebih cenderung ini setelah direnovasi semua peralatan turbin yang ada sekarang kita perbaiki prosesnya di Bandung.
We don't need sophisticated equipment with this simple machining. We can make turbine for this generate renewable energy. Yeah, actually we start since 94. Before this booming of hydropowers, roughly years we produce only 5 to maximum 6, and since 3 years ago, yeah, almost 20 to 30 units per year, ranging from 5 kilowatts to 150 kilowatts.
Economically, it is reliable, and environmentally, it's sustainable. Now, Salido Kessel is once again providing power to the national grid. It contributes to increase the stability of the electricity that is supplied to people by the grid. When all 3 turbines are restored, it will reduce around 4,000 tons of CO2 per year.
Every hour we can produce 330 kilowatt hours, which is the energy amount. And this, to produce with diesel genset, you will need about, for 3 kilowatt hours, you will need 1 liter of fuel. So actually this power plant is producing, we can say producing every hour 110 liters of fuel by avoiding it in other power plants. Every day this power plant avoiding about 2,600 liters of fuel, and the production of 3 days is 1 tank lorry.
Micro hydropower can be installed in rural areas and be maintained locally. It is an increasingly popular source of energy in Indonesia and is used both by micro enterprises and larger enterprises. Renewable energy depends upon investments and commitment. There is a huge potential of micro-hydro, but for that, financial support is needed. If properly supplied, energy makes life easier, empowers people and contributes to economic development.
In this animation, we'll look at how a hydro generator works. This is a typical New Zealand hydro station. You can see that the station has a dam, which creates a drop from one water level down to another. From outside the station, we can't see the generators. If we approach, though, we can see the power lines or conductors that carry the electricity from the station to the national grid. Each power conductor connects to a turbine-powered generator inside the dam itself. Let's go inside the dam now and look at one hydro generator to see how the power is produced. The water from above the dam flows down through pipes called penstocks. Each penstock has its own headgate at the top to stop water flow for maintenance or during an emergency. At the end of the penstock is the scroll case. This curls around the turbine like a snail shell. It's designed to create a consistent pressure of water entering the turbine from all sides. Inside the scroll case is a set of vanes called the wicket gates. These control how water flows into the turbine. The wicket gates are controlled by an external governor system. This opens and closes them in response to conditions on the national grid. A high load on the system slows the turbine. The governor system reacts by opening the gates further to speed it back up. Conversely, it will narrow the wicket gates in response to low load on the system. Beyond the wicket gates, we can see the turbine blades. The blades are shaped to extract the most possible spin from the moving water. The turbine blades and the shaft connecting them to the generator are called the runner. We will expand this into its parts so we can see them clearly. At the top is the exciter, which gets a small DC power supply from a cable attached to an external controller called the automatic voltage regulator, or the AVR. Below the exciter is the generator. The inside is a rotor, turned by the runner. The outside stationary part is the stator. This is made up of a set of 3 coils of copper wire called windings. On the rotor are a number of electromagnets, powered by the DC current from the exciter. If these are switched off, the turbine will be able to spin without generating any electricity. The magnet's poles on the outside of the rotor create a separate rotating magnetic field for each magnet. The magnets are lined up so that adjacent poles always have opposite fields to each other, north, south, north, south. As the rotor spins within the stator, each pole's magnetic field acts on the stator's windings. Each time a pole makes one full revolution, one pulse of AC power is generated in the windings and transmitted towards the grid by conductors attached to the stator. Because the stator is connected to the grid, it's important that the pulses are in time with the grid frequency. When the pulses are in time with the grid frequency, we say that the generator is synchronized. System conditions can push the stator's magnetic fields out of sync with the rotor. The difference between the movement of the stator's magnetic field and the rotor's is the torque angle. The rotor has many electromagnets on it, producing a consistent flow of power. The generator produces 3-phase power by using different conductors to carry the power generated along different parts of the stator, as shown here. This creates a 3-phase alternating current, which is represented by the sine wave.
Tidal power. Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
Barrage power plants consist of 3 different parts. 1. The barrage itself is made of concrete and holds the water back during high tide. The second part are the sluice gates. The sluice gates let water in and out during high and low tides. The third part is a conventional turbine and generator. From these 3 parts, an incredible amount of power can be harnessed. The sluice gates are left open during high tide and closed during low tide to create a water level differential. This water differential then powers the turbine while the water is released. A downside to barrage power plants is that they rely on manipulation of ocean levels and therefore have the same effect on the environment as hydroelectric dams. This means a change in the local aquatic ecosystem and a high mortality for fish. This is CGen, the world's first commercial tidal stream generator. Tidal stream generators consist of 3 basic parts. The control box monitors and engages power generation during the tidal cycle. The turbine and generator converts the movement of water into electricity, and the underwater transmission lines transfer power back to shore. As the tide moves in and out, power is generated in much the same way as windmills. The difference is that water, which is 830 times denser than air, produces more energy at lower speeds. Unfortunately, this great burst of power is only generated a maximum of 4 times a day. Tidal power, like all forms of power generation, has pros and cons. On one hand, the power produced by tidal generators is clean and renewable. The only consumables are parts and labor. Also, there are thousands of untapped sites for tidal power, containing vast amounts of potential power. On the other hand, tidal power is intermittent by nature, posing a problem for utility supply and demand. The technology is just beginning to mature, meaning project prices are very high. Finally, tidal generators can deteriorate in the ocean over time, requiring a vigorous maintenance schedule.
While Korea may lag behind in renewable energy production, its tidal power generation is second to none in the world. What appears like an ordinary park is in fact the world's largest tidal power installation built in 2011. The Sihwa Lake Tidal Power Station converts energy obtained from tides into electricity.
저희가 지금 현재 발전을 하고 있는데요. 보시면은 이 앞에 유량 조절 장치가 있습니다. 여기에 16개의 수문이 있는데요. 이 수문을 열어가지고 바닷물이 빠져나가면 수체가 돌아가면서 발전을 하는 원리가 되겠습니다.
Korea's west coast is an ideal site for tidal power generation, thanks to its high tidal range, which is the vertical difference in height between the high tide and the low tide. But as tides alone cannot generate enough electricity, an artificial setup is required. The Siwa plant makes use of a lake to increase the tidal range. A barrage was built between the West Sea and Siwa Lake with sluice gates. When the tide is low, the gates are open to empty the lake reservoir. When the tide is high, water flows from the sea into the lake via turbines.
The centrepiece, or centrepieces, are 10 giant turbines that are each 10 metres or about 30 feet in diameter. These massive blades, like this one behind me, will turn at 64 times a minute as the water flows through here at a rate of 10 metres per second. So basically, when this operation is up and running, this is the last place you'd want to be standing.
The plant boasts an impressive power generation capacity. It annually produces 552 gigawatt hours of energy, which is enough to serve 200,000 people for a year, and 1.6 times the annual output of the Soyang River Dam, the largest hydropower plant in the nation. Currently, only 5 countries, including Korea, have tidal power plants. Tidal energy has very specific location requirements, as having a large tidal range is critical. It also requires know-how and expertise, since the amount of electricity depends on when the sluice gates open and close. The Siwa Tidal Power Plant, which takes full advantage of its geographical location, looks to maintain the best operating conditions.
태양광이나 풍력은 저희가 예측을 못하고 자연이 주어지는 대로 발전하게만 되어 있습니다. 그러나 조력 발전소는 저희가 앞으로 1일, 일주일, 한 달, 심지어 1년 후까지 발전량을 예측할 수 있는 예측이 가능한 에너지가 되겠습니다. 그래서 다른 신재생 에너지에 비해서 예측이 가능하기 때문에 거기에 맞춰가지고 발전 계획을 수립할 수 있고, 그래서 같은 신재생 에너지원 중에서도 가장 최근에 좀 각광을 받고 있는 에너지.
A most promising energy solution today is to harness the kinetic power of the ocean waves and the flowing currents of sea or river. Many projects are underway and they claim to generate enough electrical energy for millions of homes without burning fossil fuels. These forces of nature are free, steady, and predictable. This video presents a new invention on various revolutionary fluid currents energy converter device by combining double-acting fluid pumping apparatuses and moving pontoon and racks to convert ocean waves or flowing currents into electricity. The two fundamental mechanical devices are the movable device and the fixed device. Double-acting piston pump. A piston is arranged to reciprocate as its piston rod is actuated by a float. When the float moves up as a rising wave passes, it pushes the piston upward and resulting dynamic flow of the fluid closes the left inlet by the ball and fluid pumped out through the center top outlet. At the same time, it causes fluid to flow through the right-hand inlet into the chamber. When the float moves down, it pulls the piston downward and partial vacuum generated at the left-hand inlet causes the top left ball to open and allow the fluid to flow in. At the same time, fluid pressure on the lower side of the piston becomes higher and it causes fluid to flow through the bottom channel into the right-hand chamber and pump out through the center top outlet. Based on the fundamental piston reciprocates working principle, many designs of energy converter can be configured. In this example, a submerged pump is operated to pump water to an elevated storage tank. Water from the storage tank is channeled to rotate a fluid motor or a turbine, which in turn rotates a generator to produce electricity. An air piston pump is disposed above the water level. The accumulator and flow control valve help to maintain a more constant airflow to drive a turbine and a generator. This design is integrated to operable both air and water piston pump. A T-shaped actuator bar is pivoted to the body of the pump such that when the float is pushed up and down by wave forces, the actuator bar oscillates about a pivot and, in turn, reciprocates the pistons. This actuator bar pump system uses the above single piston pump and a float pivoted to rise and fall with wave forces. Each pump body is configured to include two actuator T-bar piston pumps being arranged end-to-end with a sealed turbine disposed in between. The piston of two pumps is interconnected and is linked to a floating pontoon. Now a paddle is pivoted on the pontoon such that when the ocean undercurrents oscillate the paddle, it reciprocates two pistons to pump air and water in a double-acting manner. This design oscillates the actuator T-bar. On the top side of the rotary wheel, there is a crank pin or shaft that is located at a radius from the center of the rotary wheel. This piston rods of pumps are separatedly connected to the crankshaft through two link bars. The vertical rotary wheel has a plurality of peripheral aerofoil vanes and is partially submerged in a body of running water to catch the running currents and rotate. This design deploy in seabed. When water currents flow through the face of the pendulum member, a lifting force is generated and the pendulum member swings oscillate. This rotary wheel and piston pumps assembly is suspended from a boom on a mobile trailer. A plurality of one or more of the above piston pump configurations can be connected in a network. An ocean farm system comprises a number of network combinations of the above devices, be they the same, mixed, or different configurations being linked mechanically or electrically. This concept design is simple and unsophisticated, thus allowing us to harness huge unlimited renewable energy from our surrounding. If you can solve the power, you can solve almost anything.
Deep inside this mountain there hides a remarkable secret. Here, immense power is created by nothing more than water. When millions of people in the UK watch the same TV programme, be that an Olympic final, a World Cup rugby or football match, a remarkable event called a TV pickup can occur. At the end of the programme, many of us switch on our kettles, taking it for granted that the power will be there. But where will that sudden surge in electricity come from? Nuclear, coal and gas-fired power stations cannot start that quickly, and power generated from wind is unpredictable. So what's the answer? Well, it's here inside Electric Mountain, which houses one of the world's largest pump storage hydroelectric power stations. When engineers were looking for somewhere suitable for this project, they found high above Lakes Padarn and Peris at the top of Mynydd Elidir, Le Marchlin Mawr, a natural source of potential energy. This became the power station's upper reservoir. Here, the water is stored that makes the turbines turn. At the push of a button, the water can be released into the system, creating enough electricity to power a large city. When the Dinorwig quarry closed in 1969, it left deep scars on the mountain and tons of debris in the surrounding area. Some of this quarry debris was used to construct the lower dam at Llyn Peris, while the caverns that would eventually house the station were blasted and excavated from deep underground. At its peak, the Dinorwig quarry was the second largest in the world, employing around 3,000 men. By the late 60s, slate quarrying was a dying industry. After the quarry's closure, there arose a new project to build Dinorwig Power Station. During construction, over 2,500 people were employed by 33 companies. Between commissioning in 1974 and the official opening in May 1984, A staggering 2 million cubic meters of rock had been excavated. The scale of the project has cemented its place in history as one of the most significant construction projects the nation has ever seen. So now we know where it is and how it came about. Let us show you exactly what was created inside Mynydd Elidir Fawr. As we travel nearly 500 meters into the heart of the mountain and into the power station itself, you'll notice that this isn't some small track, but a proper two-way road with its own traffic light system. In all, there are 16 kilometers of tunnels that have been drilled or blasted into this mountain. In fact, if you were to strip away the floors of the main machine hall, it could accommodate St. Paul's Cathedral. You might well believe that you had stumbled into the world of Doctor Who, but these are the main inlet valves, 6 in all, each linked to one of the Norweg's giant generating units. They are among the largest of their kind ever built. Once given the instruction to start the generating, each valve can swing open in about 6 seconds, releasing the equivalent of up to 1.5 million cups of tea per second into the system. Inside each valve there are huge ball mechanisms controlled by the enormous 16-ton yellow counterweights. Despite the massive volume of water rushing through each valve, the counterweights are able to shut off the flow in as little as 20 seconds. When the water is released, it is directed towards and through the turbines via a spiral casing which gets smaller and smaller in diameter, thus creating enormous pressure with which to drive the turbines at up to 500 revolutions per minute. A conventional thermal power station can take as much as 12 hours to get up to speed. Even a station on standby will take at least 45 minutes to get to full capacity. The Norweg, on the other hand, is unique in that it can be supplying power not within minutes, but within seconds. It can go from zero power to full power in only 12 seconds, making it one of the fastest acting power stations in the world. The turbine generators in most power stations are installed horizontally and take up enormous floor space. At the Norweg, they stand vertically. Each turbine is connected via a vertical shaft to its own generator, and as the water begins to turn the turbine, the shaft rotates the generator's huge central rotor, creating the electricity for instant delivery into our homes and businesses. Instructions are received from the national grid, and power is generated instantly, in large part due to the position of the upper reservoir, Marchlin Mawr. On a daily basis, the level can drop as much as 37 meters, as 7.6 million cubic meters of water from the reservoir are available to drop some 568 meters, nearly twice the height of the Empire State Building, and travel over 2 kilometers into the lower Llyn Peris. By the time the water has emerged from the power station, it could have helped to generate up to 1.7 gigawatts of power. Of course, once the stored water has been released, it needs to get back up to Marchlin Mawr so that its availability to generate can be re-established. This is done at night time when there is no great demand for electricity. The plant is simply put into reverse. The generator becomes a motor, and all the water that has come down during the day is pumped back through the system, using the same turbines as pumps, this time turning anti-clockwise. Simple and brilliant at the same time. It is astonishing to think that this huge complex exists and yet is not visible to the naked eye, a simple idea that became a brilliant reality. Its role in the future, as we move towards a low-carbon electricity system, is assured. It will continue to meet the rapid surges in demand that we require, as well as providing the necessary backup when the wind does not blow. So, join us as we travel deep into the mountain that houses the Norweg Power Station, the Electric Mountain.
Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydroenergy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream.
choose its own way. If you could just hold me now, 'cause I don't know how to